So let us start for the first question today. It is from GATE 2021 Instrumentation Technical Question 27. So this question is from electrical machines. So a single phase transformer has maximum efficiency of 98%. The core loss are 80 watts and the equivalent winding resistance as seen from primary side is 0.5 ohms. The rated current on the primary side is 25 amperes. The percentage of the rated input current at which maximum efficiency occurs is. So four options are given. The first is 35.7%, 50.6%, 80.5% or 100%. So let us see what is the useful data to solve this question. The efficiency of the transformer can be calculated from the following equation, where percentage efficiency is 100 into output power P naught upon output power plus copper loss and core loss. So let us define the efficiency in terms of full load power. So again, percentage efficiency is equal to 100 into X is the fraction of the full load power. So X into full load power upon X into full load power plus X square into copper losses plus P core. So core losses are termed as constant losses. They are independent of the load or the loading that is the transformer is experiencing, and X square is coming with copper losses because copper losses are I square R losses, in which X is the percentage of the load current when I square R is done. So that's why X square also comes in copper losses. So let us find the condition for maximum efficiency, which is we have to find the value of the X. So by differentiating the equation which we saw, the loading equation that we saw for efficiency, differentiating with respect to X, we get an equating to 0. So the expression we get is this, a long equation, and when we simplify this, we get P core is equal to X square PCU. Therefore, the value of X that comes out is under root P core upon PCU. Okay. So now, as I said, PCU, that is the copper loss, is I square R into R primary, and let us calculate it for full load. So full load current is given in the question as 25 ampere. So PCU is equal to 25 square into 0.5 ohms, that is the resistance that is given. Equivalent winding resistance seen from the primary side is 0.5 ohms. So PCU is equal to 25 square into 0.5, that is 31.312.5 watts. Therefore, X is, as seen from the previous derivation, the condition for maximum loading, the value of X is under root P core upon PCU, that is under root 80 upon 312.5, that is 0.506 is the ratio X. So if we convert this X into percentage, that is 50.6 percentage of the rated current or the rated power is needed to achieve the maximum efficiency. So therefore, 50.6, option B is the answer to this question. So as no one is there in the meeting, I will be proceeding with the next question. So again, the next question is from machines. So GATE 2021 Instrumentation Technical Question 28. A slip ring induction motor is expected to be started by adding extra resistance in the rotor circuit. The benefit that is derived by adding extra resistance in the rotor circuit in comparison to rotor being shorted is A. Is the starting torque will be higher. Second, will the power factor at start will be lower, or is the starting current higher, or whether the losses at the starting will be lower. So which of the option is correct? So let us just see the relation between the power and torque. So power is equal to torque into angular speed, which is known as omega. And based on the equivalent circuit at the bottom of the slide of the induction motor, the equivalent resistance that represents the rotor is RR dash, which is referred to the stator side, rotor resistance, upon S. So RR dash upon S is the rotor power that is seen. Then if you rearrange this term into I square R kind of to calculate the I square R losses and the mechanical power, you can split this resistance into these two terms, which will correspond to copper losses in the rotor and which will contribute to the mechanical output power. However, this is of irrelevance for this question. We shall be focusing on this. So P rotor is proportional to R rotor upon S. Now, at standstill, which is at the start, the NR is 0, where rotor is not rotating. So slip is equal to 1, where slip is given by the formula S is equal to Ns minus Nr upon Ns. So Nr is equal to 0, so Ns by Ns, S equals to 1. Now power in the rotor circuit can be expressed as torque rotor, basically torque developed by rotor, is proportional to torque developed by the rotor is proportional to P rotor. Now as this is a AC equivalent circuit and AC quantities are being involved, so torque developed by rotor will be equal to, let us add a proportionality constant here, K, to remove this proportionality sign, and P rotor will be denoted as ER into IR into cos phi, where ER is the rotor voltage and IR is the rotor current and cos phi is the power factor between the voltage and the current. Let rotor circuit impedance will be denoted by equivalent R and X, and frequency at which rotor impedance experiences the impedance is determined by the slip. So basically rotor is having a voltage induced at a slip frequency, that's why this S is coming. But however, at standstill S is equal to 1, because the rotor is not rotating at the starting instant, S is equal to 1. So IR is equal to ER by Z, basically voltage upon impedance. So cos phi will be also similarly RR upon under root RR square plus XR square, where S is equal to 1 here at standstill. So this is the standstill power factor. Now when we put this in this equation, K into ER IR cos phi, we get the equation as torque in rotor at the starting instant is K into ER square upon RR into RR upon RR square plus XR square. Similarly, as we saw in the previous equation where we calculated the condition for maximum efficiency for transformer, similarly when we differentiate this equation of the torque for calculating the maximum torque condition, it comes out to be rotor resistance equal to rotor impedance. Okay, so usually impedance, as it is a magnetizing inductance, so motor is a highly inductive kind of a load, rotor resistance is usually lesser than rotor impedance. So therefore when we add extra resistance to rotor, this condition can be satisfied to get maximum torque at the starting. Therefore the option that directly matches our derivation is the starting torque will be higher, because we are able to achieve this condition RR equal to XR. Now let us see why these other options are wrong. So power factor at the start will be lower. So if we add extra resistance, let us look at the power factor expression. As we know, RR is coming in the numerator and XR is already there. So when we increase RR, it is observed that the overall power factor is increasing, because it is the resistive nature of the circuit is increasing. Therefore power factor will increase, it will not decrease, it will not be lower. Starting current is higher. As we saw, rotor current is ER upon ZR, and ZR is RR plus S square XR square, S is equal to 1. So when R is increasing, Z will increase, and therefore I rotor will be lower as ZR is increasing. So therefore the starting current will be lower. So this option is also wrong, and losses at the starting will be lower. As we are adding a resistance in the circuit, the resistive losses will increase. So therefore the losses at the starting will be higher. So the losses won't be lower here. So based on this options, based on the derivation, we proved that the starting torque will be higher, and based on the similar derivation, intermediate derivation factors, we proved that these three remaining options are wrong. Therefore, A is the correct option to this question. Okay, let us move to the next question. So it is GATE 2015 session 2 electrical technical question 19. So the current I in amperes in the 2 ohm resistor of the given network is. So the circuit is shown, it is powered by 5 volt source, and multiple 1 ohm resistors are connected in a crisscross fashion, and a 2 ohm resistor is given. So now let us look how much will be the current through this 2 ohm resistor. So let us rearrange the circuit. This circuit is rearranged to get an equivalent circuit like this. So 1 ohm, and in center it is 2 ohm resistor. So it forms a kind of a H, 90-degree rotated H bridge, which we typically call it, and this is the voltage between the two terminals. Before we solve numerically by assuming I1 in this loop, I2 by this loop, let us proceed by a normal approach. Let us assume that 2 ohm resistor was not there here. So assuming 5 volt is across both the bridges, 1 ohm is equivalent. So at this intermittent point, the voltage would have been 2.5 volt and 2.5 volt. And when we check the potential difference between two terminals, it is 0. So if we had added a resistor or a conductive path here, then also the current wouldn't have been flown in this path. Now let us assume if this resistor is made as 4 ohms. Okay, so the potential at this intermittent point would have been 1 volt with respect to this 0 volt node, and similarly for the other path again. So this 1 volt and 1 volt, the potential difference will be 0 volts. Now again, if we change this upper branch to 8 ohms and 2 ohms, still the potential drop will be 1 volt, however in both the bridges. However, the current drawn by each bridge will be different. So again, when we see the relative potential difference between two nodes, it will be 0 volt. So when there is 0 volt potential difference, there won't be any current flow in this path if we add any resistance. So as by the nature of the resistance, current through resistor is flown from point of higher potential to lower potential. So as there is no potential difference, even if we add a resistance here, there won't be any current through this path. So we can generalize this what analysis which we saw, that if the ratio of R1 is to R2 and R3 is to R4 is equal, the potentials at these 2 points are essentially constant if this ratio is maintained, and therefore no current will be flowing through this central H path, where that is the 2 ohm resistor, and that's why this is called a typical Wheatstone bridge, that is called a H bridge, and no current will be flowing through this 2 ohm resistor if this ratio is maintained. And in the given question, the ratio is 1:1 for this 1 ohms resistor. Therefore, the current through this 2 ohm resistor will be 0. Okay. So I would like to conclude this meeting, and I'll be sharing this recording in the GATE portal subsequently. Thank you.